Hello everyone and welcome back to my channel Gyan Sampada. In our previous class we have discussed about spin-lattice relaxation as well as derived the relation for the build-up magnetization involving spin-lattice relaxation time. So based on the same, we are going to continue our today's class where we will be dealing with relation between susceptibility as well as spin-lattice relaxation time. So if you have not gone through the previous class, first go through it because the numbers of equations we have used in the previous class will be carried on and used in today's class. So let's start our today's class on the continuation part of spin-lattice relaxation. So now let us find out the relation between susceptibility chi at high frequencies and tau 1, which is the spin-lattice relaxation time. We know that the order of tau 2 is very much small than tau 1. So tau 1 is greater when compared to tau 2, where tau 2 is the spin-spin relaxation time. So for that case, the spin system may be assumed to be in thermodynamic equilibrium, which means the spin system may be treated as a separate system itself because it is acting as an isolated system. There is no exchange of any parameter with respect to the neighbors. So we can say that this separate system has its own specific heat as well as certain spin temperature denoted as Ts. S stands for spin system. So this is on application of static field. But when an oscillating magnetic field is also applied parallel to the applied static field to the paramagnetic salt, then the spin temperature Ts will also start oscillating and it will change from the constant temperature of the lattice. So if the constant temperature of the lattice is denoted as TL, L stands for lattice, then the application of oscillatory magnetic field is going to create the difference between the temperatures of the spin system and the lattice. So we can say there is a difference between Ts and TL which will be reducing because of the thermal contact between the spin and lattice system. So it is happening something like if we are applying the oscillating magnetic field to the system, the spin systems are going to start oscillating. So the spin systems will change its temperature, and as the spins are within the lattice, the temperature of the lattice and temperature of the spin system is going to be different. So this is something like a non-equilibrium state. So if it has to come back to its equilibrium position means throughout the temperature has to remain almost same. So Ts and TL should be approximately equal to each other. And if that has to happen, then there should be a thermal contact. So there is a thermal contact between the spin system and the lattice, and thus there will be exchange of the energy or heat which is going to reduce the difference in temperature of the spin system and the lattice, that is Ts minus TL. And this type of interaction is called as spin-lattice interaction, where both spin and lattice are involved to bring back the system into equilibrium. And larger the spin-lattice interaction, smaller will be the temperature difference. So we can say if temperature difference has to be equal to 0, then spin-lattice interaction has to be greatly pronounced. So this is one factor. And also another factor which is going to influence the difference in the temperature of the spin system and the lattice is the period of the oscillatory field. So oscillatory field, whichever we are applied, which is responsible for the non-equilibrium of the system, that is also responsible for this difference. So generally the period of oscillatory field is taken to be equal to tau, which is equals to 2 pi by omega, where omega is the frequency of the oscillatory field. So that is also going to influence this interaction. So as the frequency is also going to influence, let us find out what happens at different frequencies. So first, at low frequency, what happens to the system? So when there is a low frequency, it means omega is low, and omega is nothing but 2 pi by tau, where tau is the period of oscillatory field. So when frequency is low, it means period is high. So tau is very much greater when compared to spin-lattice relaxation time tau 1. In that case, the temperature of the spin system and the lattice will be equal, because the difference will arise when there is a spin-lattice relaxation. So here the field whichever we have applied, it is having the greater period when compared to tau 1. So both the temperatures are going to be equal, that is already the equilibrium is set up, and thus we can say the susceptibility will have its static value or the isothermal value, and let us denote it as chi naught equal to chi t, that is static value at low frequency. So this is the first case, and moving to the second case is if tau is very much less when compared to tau 1, that is at higher frequencies. So in that case, no heat exchange will take place between the spin system and the lattice system. So no exchange of heat means it is something like an adiabatic process. So susceptibility is said to have its adiabatic value denoted as chi s. So we can say here, moving from low frequency to higher frequency, that is from higher period to the lower period, we can observe that susceptibility is going to vary from chi t to chi s, that is isothermal to adiabatic value. So clearly we can observe the frequency of oscillatory field is also going to influence this important factor. Clearly we can observe that frequency of oscillatory field is responsible for gradual change from chi t to chi s. So omega increases means tau decreases, that is chi t to chi s. So as we are explaining about isothermal, adiabatic, we can relate it to thermodynamics. So again we are going to apply thermodynamical equation where chi t and chi s will be involved. So the standard equation is something like this, where Ch is the specific heat at constant field, H is the field, and Cm is the specific heat at constant magnetization. So that can be given as Ch is dou H by dou m at S, which means the adiabatic value. So the susceptibility is nothing but m by h. Generally we write chi is equals to m by h, but here we are having dou H by dou m, which is inverse of m by h. So it will be equal to chi s in the denominator, and in the numerator we are having chi t. So let us call it as equation number 7. Then another important equation was given by Casimir and Dupré, and these two people said that the rate of heat exchange, which is dq by dt from the lattice system to the spin system, was directly proportional to the temperature difference between the systems. So dq by dt is directly proportional to Ts minus TL, which we can write it as dq by dt is equals to minus alpha into Ts minus TL, where alpha is the constant which describes the degree of thermal contact between the spin system and the lattice. And here this temperature difference is taken as theta. So let us call it as equation number 8 for further simplification. Again using the thermodynamical equation, which involves magnetization, static field, temperature, charge, heat, etc. So the relation is TdS is equals to Cm dt minus T into dou h by dou t at constant m into dm. So here we are having dq, and according to thermodynamics we know that dq can be written as T into ds, whereas is the entropy, T is the temperature. And from the above equation, that is equation number 8, dq can be written as minus alpha into theta into dt. So just substituting that value, we are going to get equation number 9. And in order to solve this, we need the solution for h and m, and since h of t is equals to h plus h1 e raised to I omega t and m of t is equals to m naught plus chi h1 e raised to I omega t, that is static field plus alternating field and static magnetization plus alternating one. Because we know susceptibility is m by h, so m will be equal to chi into h. So here it is h1. In this manner we can write the equation for field as well as magnetization, and both are relating to the temperature difference theta. Since these two things oscillate with an angular frequency omega, the temperature difference theta will also oscillate with the same angular frequency omega, and thus we can write theta is equals to theta 1 into e raised to I omega t, which is considered as equation number 10. So now we are having the solution for theta, we are having the equation number 9 which involves theta. So finally we can substitute the value in equation number 9 so that we can get minus alpha theta 1 is equals to I omega into Cm theta 1 minus T dou h by dou t at constant m into chi h1, that is the dm. So just we have substituted the value of theta in equation number 9. So here dt is nothing but change in the temperature, that is nothing but Ts minus TL, which can be written in terms of theta 1. And as such we can say that the magnetization is a function of magnetic field which is applied as well as the temperature. Thus using chain rule we can write a dm as dou m by dou h at constant t into dh plus dou m by dou t at constant h into dt. So this is according to the chain rule which we consider in mathematics, and dm is nothing but chi h1, dh is corresponding to the oscillating field, dt is corresponding to temperature difference, that is theta 1, which we call it as equation number 12. So from equation 11 and 12 we are going to eliminate theta 1 so that we will get the equation for susceptibility. Because as such susceptibility is corresponding to magnetization and magnetic field, so the temperature term can be eliminated from equation 11 and 12, which leads us to chi is equals to dou m by dou h at constant temperature into Cm plus alpha by I omega divided by Cm minus T into dou h by dou t at constant m into dou m by dou t at constant h plus alpha by I omega. So just rearranging some of the things using previous equations which we have seen, we will get this equation. And if you look at the denominator, we have Ch minus Cm is equals to this factor. So we can write Cm minus this factor as just Ch, that is specific heat at constant field. So the whole equation is simplified as chi is equals to chi t, that is dou m by dou h is chi at constant temperature means isothermal value into numerator as it is divided by the whole term is Ch plus alpha by I omega as it is. So let us call it as equation number 13. Now clearly we can observe that susceptibility is a complex term. So there is some real part as well as the imaginary part, and for that we need to just separate these two parts, that is equating the real and imaginary parts, that is taking the LCM using the previous values, we can get the values for chi dash and chi double dash, because chi is a combination of chi prime as well as I chi double prime. So there we can just separate chi prime and chi double prime, that is the real part and imaginary part, so that we get these two values for chi prime as chi s plus chi t minus chi s divided by 1 plus omega square tau 1 square, and chi double prime is chi t minus chi s into omega tau 1 divided by 1 plus omega square tau 1 square. So this is corresponding to the imaginary term and this is corresponding to the real term, which we have obtained by separating equation number 13. And here tau 1 is nothing but Ch by alpha. So wherever we got Ch by alpha, we have substituted as tau 1, which is spin-lattice relaxation time. So this is a very important equation which explains about the susceptibility corresponding to the spin system. And now clearly we can observe that real and imaginary parts of susceptibility are function of omega, which is the frequency of oscillating magnetic field. And as such, tau 1 is fluctuating between the order of 10 raised to minus 2 to 10 raised to minus 6 second. So almost everything is remaining as it is, whereas omega is the main dependence on the susceptibilities. So now we are going to consider the cases for low frequency as well as high frequency. So if we are having low frequency, that is omega is small, in that case we can say that chi prime will be equal to chi t, because if omega is small, we know tau 1 itself is small, squares of the smaller numbers is very negligible, so that it is neglected with respect to 1. So chi t minus chi s by 1 will be there. So chi s minus chi s will get cancelled, so that we observe chi prime is equals to chi t, and in that case chi double prime will remain 0. That is the case for lower frequencies. And if the frequencies are higher, in that case chi prime will be equal to chi s, that is the adiabatic value, because higher frequency means omega is greater, omega square is still more greater. So 1 by a greater number is almost a very small number, so that chi prime will be equal to chi s, and again chi double prime is going to remain equal to 0. So to understand more clearly, we can plot a graph of chi as a function of omega into tau 1, which is the common factor in both the formulae. So along x-axis we are having omega into tau 1, along y-axis we have one side chi t, another side is chi s. So as such, if we observe, chi prime is a combination of both chi s as well as chi t, but at lower frequencies we can say chi prime is equals to chi t, and at high frequencies chi prime is equals to chi s. So this is the chi s value and this is chi t value. This is the nature of graph for chi prime. And if you move for chi double prime, then we can observe that at lower frequencies chi double prime is 0, at higher frequencies again chi double prime is 0. But slowly it goes on increasing, reaches the maximum and again starts decreasing and reaches 0 at higher frequency. And when omega tau 1 will be equal to 1, at that situation chi double prime is having the maximum value. So omega into tau 1 is equals to 1 means omega is equals to 1 by tau 1. So whenever omega is equals to 1 by tau 1, chi double prime will have its maximum value, that is the peak value. And clearly we can observe that chi prime is having a greater value because of this plus sign, and chi double prime is having a smaller value. And chi prime at lower frequency it is almost constant, and when omega is equals to 1 by tau 1, it goes on decreasing and again attains some stable value which is equals to chi s. And this is the value of chi s which is almost 25% of chi t. So if chi t is from this extent till here it is 100%, then chi s will be just 25% of chi t. So we can say chi s is equals to 0.25 chi t. So that is the another feature which can be observed from the nature of graph. And whenever we are applying a static field as well as an alternating field, we observe the energy absorption, and this is the nature of graph for the energy absorbed by the substance due to spin-lattice interaction, whereas if there is spin-spin interaction, then this is the nature of graph for energy absorbed or attributed to spin-spin interaction, which is denoted as A dash, and that is going to work at higher frequencies only. At lower frequencies, spin-lattice interaction is dominant one. So if interpretation of graph is clearly picturized in mind, easily the whole derivation and interpretation of the data can be remembered. So in the last two classes, we have discussed about spin-lattice relaxation, that is starting from the condition to the derivation, as well as got some of the details or cases and conditions for the spin-lattice relaxation with the graphical interpretation for easier understanding. So in our next class, we will be dealing with the spin-spin interaction, that is spin-spin relaxation, which is another type of relaxation phenomena. Till then, study well, stay tuned, and thank you for watching.